Good morning, all of you. So we are meeting after 3 years. 2020 we met last time, and in these 3 years, some infrastructure development is there in IIT Kharagpur. So this is the new entrance gate, and today I am going to talk about plasmid under macromolecular crowding. So the two keywords are there: macromolecular crowding and plasmid. So in few slides, I will discuss about crowders and what are the plasmids we have taken in the experiment. So this is totally experimental work. So I will start with acknowledging some people. So I one part of the work was done in my postdoc. So in Singapore with Professor Johan, and we have taken different plasmid, and we did a small angle neutron scattering with that. Okay. And we have some collaborator across the department within the institutes, and you can find Burada in the audience, and Professor A. Ganguly, who is in the biotechnology department, and he helped us to prepare the plasmids. And this work, what I'm going to present here, is totally done by Anurag and Suparna, and they are graduated now, and they are doing postdoc in USA. And also, I should acknowledge funding agency DST. Okay, so start with macromolecular crowding. So when you look at the big picture of the cell, then you have so many cell organelles, and those cell organelles are also surrounded with the very fine particles, biomolecules. So it may be small lipids or glucose molecules or so on. So in vitro, how you can mimic those environment? So suppose you have a test DNA, and then you can place the crowders, which is very small, tiny in sizes. So that also depends on the shape. You can use different shape of crowder and different size of the crowder. So what are the common crowder we can use in vitro? Here a few name we have mentioned, but there are a lot of crowders available in the market. You can use any of them. So dextran is neutral macromolecules, and it varies with different sizes. You can use ficol, PEG, and glucose, fructose, or sucrose molecules. So in this experiment, we have used dextran molecule of different molecular weight, starting with very small one, 5 kDa, 50 kilodalton, and 4 kilodalton. And the volume fraction we have used from 1% to 15%. So if you go beyond that, then you can find the condensation of the plasmid. So we have stopped that experiment after 15%. So these crowder, what it does, it reduces the molecular dynamics, and it enhances the different interaction, and also you can see the volume exclusion, and it also changes the property of the solvent, but within this volume fraction the viscosity does not change. So we are not changing the quality of the solvent. So what is plasmid? So this is very small and circular uh, double helix DNA. So you can see here it is slightly different than the bacterial DNA, and it can also have different supercoiling. So it is not only the circular, but it can also have supercoils. So in this whole experiment, we have taken 4 different kind of plasmid, starting from 2.6 kilobase pair to 5.3 kilobase pair, and we have employed laser light scattering experiment, where you have a detector. You can measure the scattered intensity, the fluctuation of the intensity from this plasmid, and if you have a correlator, then you can also measure the correlation function, and you can derive the diffusion constant. So diffusion is the main key parameter, and from there you can derive many other parameters about the macromolecules. And if you vary the detectors with a different angle, then you can also measure the static property of the macromolecules, like second virial coefficient and radius of gyration. Okay, so As you know, if you track the particle, then you can measure the mean square displacement, and if it scale with linearly with the time, then you have a normal diffusion, and if this alpha is less than 1 or greater than 1, you will be having subdiffusion or superdiffusion respectively. So this is the gist of the talk. So when you increase the size of the plasmid, since we have taken 4 different plasmids starting from 2.6 kilobase pair to 5.3 kilobase pair, and if you increase the crowding volume fraction, so it start with, so there is a so we have placed in the circle, and here you have a in cylinder. Okay, so this at the low concentration of the crowder, it is following normal diffusion, and when you increase the concentration of the crowder a bit, then it changes to the subdiffusion region, and it also changes their shape. So it migrates from the Gaussian coil to rod like structure. So what is the application of this crowding? So it also involved in the protein folding, DNA condensation, liquid phase separation, and compaction and condensation are two different things. Okay, so if you increase the volume fraction of the crowder more than 15%, then DNA condensate, means it form different phases. Okay, so large DNA molecule undergo a transition between an elongated conformation to a very compact form. So the application also includes the gene delivery. So we are not talking about this. Okay, so some previous result. So before doing some positive experiment, so what we did, we have to check the background scattering. So what is the contribution of this crowder? So if you mix the crowder in the DNA solution, then we are just checking whether what is the contribution of the intensity contribution from the crowder. So we check the molecular mass of the DNA, and it is very much consistent with the theoretical value. So less than 10% variation we found. So we are sure that most of the scattering intensity is coming from the DNA. So when you measure the radius of gyration and with the volume fraction, then it scale with 5 raised to minus 1 by 4. So this is 5 is volume fraction you have, and you can see here the radius of gyration for a small crowder. So for 2.6 nanometer dextran particle, it increases, the radius of gyration increases. It means it go inside that plasmid and it swells up. Okay, so initially it increases, and same thing happened for slightly bigger one for 50 kD dextran molecule, but for higher size for 70 nanometer, start from the beginning, it compact the DNA molecule. Okay. So what is the contribution we have? So you can also measure the elastic pressure and osmotic pressure. There will be balance of osmotic and elastic pressure, and a scaling relation, like how Rg scale with volume fraction. So if you can use phi as rho d raised to 3 and so on. Okay, so this is the important result we have. So what we are showing here, we have 3 different plasmids. So this is PBS and this is PCMB. So different molecular weight of number of base pairs are there. So you can see here.
2 more minutes.
Okay. Okay. So you can see when you increase the volume fraction of the plasmid, so you can see a blue shift here. Okay, so for the small crowder, it require higher volume fraction, and you can see the fitting is having 2 different regimes. So the compaction happens in 2 different regime. Same thing for all 3 different plasmids. Okay. And here we are plotting gamma versus phi dextran size. So this scale with Rg phi raised to minus gamma, and gamma is 1 by 1 plus x. Similarly, this alpha is what we call uh, we I told you in the diffusion slides that if alpha is equal to 1, then you have a normal diffusion, and if it is less than 1, then it is comes under subdiffusion. So we measure that one, and up to this 0.9 and above, it is normal diffusion, and below this one is subdiffusion, and this is plotted for alpha versus phi for all three different plasmid. And you can see here again very similar trend you have. So for a small plasmid, most of the data are in the normal diffusion, and if the size of the crowded is higher, then it restricts the motion of the DNA molecule, and it comes under the subdiffusion. And you can also measure the second virial coefficient, which is indirectly representing the interplasmic repulsive interactions, and it also gives you depletion attraction. So how you can measure that? You can vary the concentration as well as the angle. So you can have 0 angle and 0 concentration, that will give you the value of second virial coefficients. And here you can see here the second virial coefficient with the external size. So it decreases as you increase the size of the crowder. This is very important result we have. So as you know, the translational diffusion constant is varies as m raised to just you have 1 over m. Okay, here we split it into two parts, so epsilon and sigma. So epsilon is for the you can have for different shape. So for rigid rod, epsilon is 0.8, and for Gaussian coil you have 0.5, and this delta is for the excluded volume exponent. And you can see when there is no
Time
crowder,
is up.
then it started from okay. So this is the conclusion slide. So I can take 1 minute. Okay, so this crowding may show swelling or compaction of macromolecule. It depends on the size and concentration of the crowder. Plasmid conformation depends on excluded volume effect, entropy maximization of the crowder, selling of interplasmic repulsive interaction by crowder, and also I have shown you second virial coefficients and translational diffusion constant, how it varies with the sizes of the crowders, and this is a scaling general scaling form we have to type. So thank you for your kind attention.